Welcome dear learners. We are studying quantum chemistry and now we are discussing the rigid rotator, the second part. In this module, we are discussing the phi and theta equations of rigid rotator, the complete solution to the theta equation, Legendre and associated Legendre polynomials, the complete wave function of the rigid rotator, the energy of rigid rotator and spherical harmonics. First of all, the rigid rotator. A diatomic molecule rotating about an axis perpendicular to internuclear axis passing through the center of gravity of the molecule constitutes an example of a rigid rotator. See the pictorial representation. Here, this is being a diatomic molecule. The first atom having mass m1 and the second one is having mass m2. The center of gravity is shown here and the distance from first particle to the center of gravity is taken as r1 and the next distance, that is from center of gravity to the second particle of mass m2 is taken as small r2, and there is an axis of rotation as well as internuclear axis. The molecule executing rotational motion with respect to an axis passing through the center of gravity of the molecule. Now, the Hamiltonian operator of the rigid rotator. We already learned in the first part that the Hamiltonian operator consists of only kinetic energy term, and we have the Hamiltonian operator H hat is equal to T hat plus V hat, where T hat represents the kinetic energy part and V hat represents the potential energy part. Since we are describing the rotational motion of a particle, we can take V hat is equal to 0 and H hat diminishes to T hat, and T hat or kinetic energy operator will be equal to L square hat divided by 2I. This part we have discussed with the first section. That is, we are getting the Hamiltonian operator of a rigid rotator equal to S hat equal to L hat square divided by 2I, where L represents angular momentum and L is equal to I omega, where I represents moment of inertia of the molecule. Mu is equal to I is equal to mu r square and mu represents reduced mass of the system. All these parts we have discussed in detail in the first section, and we have finally S hat is equal to L square hat divided by 2I. Thus, on putting the value of L square hat in spherical polar coordinates, we will get H hat of the Schrodinger wave equation of the rigid rotator as minus S cross square by 2I 1 by sin theta dou by dou theta of sin theta into dou psi by dou theta plus 1 by sin square theta into dou square by dou phi square. This is being the Hamiltonian operator of the rigid rotator system. Now, the Schrodinger wave equation for a rigid rotator. We have the Hamiltonian operator as S hat equal to minus S cross square by 2I 1 by sin theta dou by dou theta sin theta dou by dou theta plus 1 by sin square theta into dou square by dou phi square, and we have the time independent Schrodinger wave equation Hamiltonian psi is equal to E psi, and this substitution of this H hat value here leads to the complete Schrodinger wave equation for the rigid rotator as 1 by sin theta dou by dou theta sin theta into dou psi by dou theta plus 1 by sin square theta dou square psi by dou phi square plus a2 by square I by h square into E psi is equal to 0. This is the Schrodinger wave equation. This we have solved previously. For the phi equation, we adopted the method of separation of variables, and we are now simply sifting through all this area for just remembrance. And first of all, we have to deal with the separation of variables, and this Schrodinger equation already contains two variables, namely the theta variable and the phi variable, and we have to adopt the method of separation of variable. For this, we are taking the assumption that psi of theta phi is equal to theta of theta into phi of phi. This can be separated by the method of separation of variables, and on substituting and rearranging, we get sin theta by theta dou by dou theta of sin theta into dou theta by dou theta plus a2 by square I by h square into sin square theta equal to minus 1 by phi dou square phi divided by dou phi square. We can equate both the sides, say to m square, there obtaining two differential equations, each in one variable, these equations are simply termed as the phi equation and the theta equation. Thus, we get the phi equation of the rigid rotator as dou square phi divided by dou phi square plus m square phi is equal to 0, and the theta equation as 1 by sin theta into dou by dou theta of sin theta into dou capital theta by dou small theta plus lambda minus m square by sin square theta into theta of theta is equal to 0. Here lambda is a parameter that is equal to 8 pi square IE divided by h square. So these are the theta equation and phi equation. We already learned about the complete solution of the phi equation. It's a normalized solution, that is phi of phi is equal to 1 by root of 2 pi into e raised to im phi, that we already covered in the first part of the rigid rotator case. Now we are going to discuss the complete solution of theta equation. We have one method of separation of variable of the Schrodinger wave equation for a rigid rotator. We got the theta equation as theta equation equal to 1 by sin theta dou by dou theta sin theta into dou theta by dou theta plus lambda minus m square by sin square theta into theta of theta is equal to 0. We know we have to keep in fact that lambda is a constant here, that is theoretically equal to 8 pi square I divided by h square, assuming for the sake of simplifying this equation, assuming x as a new function and x is equal to cos theta. Since theta has range from 0 to 2 pi, that is 0 less than or equal to theta less than or equal to pi, we have to set the limit for x based on this relation. That is, x has a limit from minus 1 less than or equal to x less than or equal to plus 1. That means x ranges from minus 1 to plus 1, but theta ranges from 0 to pi. And we are setting the limit of x based on this relation, that is x is equal to cos theta. Also, we are taking the assumption that theta of theta present in this equation is switched over to px, where px is a function of x. So we are using the assumptions x is equal to cos theta and x has a limit from minus 1 to plus 1, and theta of theta must be replaced by px, where px is a function of x. By incorporating all this, we can modify this equation into a new form. Thus, we are getting the modified form as 1 minus a square d square p by dx square minus 2x into dp by dx plus lambda minus m square by 1 minus a square into px is equal to 0. This one is a simplified equation, and here the variable is x. We have to keep the fact that x is related to theta, x is a function of theta, x is equal to cos theta. Moreover, let lambda is equal to L into L plus 1. We are now making one more substitution in this equation. We are just replacing lambda present in this equation by L into L plus 1. That is, I am putting lambda as L into L plus 1. Therefore, this equation takes the new form, that is 1 minus a square d square p by ds square minus 2x dp by dx plus lambda, that is replaced as L into L plus 1 minus m square by 1 minus x square into px equal to 0. And I marked this equation as equation number 1, and this equation 1 is very important, and this is known as the so-called Legendre equation. So, equation 1 is called Legendre equation. We are making this much modification to the theta equation for the fact that if you are getting the Legendre equation, we will have a solution for Legendre equation that we can adopt from mathematics. For that, we are modifying the original theta equation into this Legendre form. Thus, the Legendre equation is once again 1 minus a square d square p by ds square minus 2x dp by dx plus lambda L into L plus 1, L into L plus 1 minus m square by 1 minus s square into px is equal to 0. Keep this equation always for your reference, and this equation is very important, and that is nothing but the Legendre equation. This equation will again appear in front of you whenever we are discussing the hydrogen atom problem. The same kind of Legendre equation will also appear in the case of the hydrogen atom problem. Now, we have to discuss further about the solution of the theta equation. We learned about the Legendre equation. Legendre equation 1 has solutions, and the solutions of which are known as Legendre polynomials and Legendre functions. That is, two sets of solutions are there. The two sets of solutions of equation 1 or Legendre equation are simply known as Legendre polynomials and Legendre functions. More correctly, these Legendre functions should read as associated Legendre functions. We can enter into details of Legendre polynomials and associated Legendre functions. Now, solutions of equation 1. Equation 1, that is previously known as the Legendre equation. This is Legendre equation. The solution of this Legendre equation when m is equal to 0. Here we can see the presence of m, and for m is equal to 0, this Legendre equation has a solution, and that solution are called Legendre polynomials. So what are Legendre polynomials? It's very important. We have Legendre equation. The theta equation of the rigid rotator is known as the Legendre equation. Legendre equation contain a parameter m. When m is equal to 0, Legendre equation has some solution, and the solutions of Legendre equation when m is equal to 0 is known as the Legendre polynomial. Legendre polynomial is denoted as PLX. We know x is equal to cos theta. Therefore, PLX can be represented as PL cos theta. Legendre polynomials arise in a number of physical problems, and hence Legendre polynomials are very, very important. So, on concluding, we can say that Legendre polynomials are solutions of Legendre equation one and only if m is equal to 0. If m in the Legendre equation is 0, its solution are termed as Legendre polynomial, denoted as PLX or PL cos theta. Now, we can have first few Legendre polynomials here. Legendre polynomials have different values. The values depends on L also, and first few Legendre polynomials obtained are shown here, and this is obtained by putting different values for L, and if I put L is equal to 0, the Legendre polynomial will be P0x, and that is numerically equal to 1. And when L is equal to 1, the Legendre polynomial can be denoted as PLX or simply L is equal to 1, so P1x. P1x is equal to x. X is nothing but cos theta. And if L is equal to 2, we are getting P2x, and P2x is numerically equal to half of 3 square minus 1. And if L is equal to 3, we get P3x, that is simply half of 5s cube minus 3x. And for L is equal to 4, we are getting P4x, and its value is 1 by 8 into 35x raised to 4 minus 30x square plus 3. This about first few Legendre polynomials. Once again, Legendre polynomials are the solutions of the Legendre equation when m is equal to 0. The enlisted chart that consists of first few Legendre polynomials, and these values are obtained by putting different values for small l, that is L may be 0, 1, 2, 3, etc. We can also get different values for different other values for Legendre polynomials, and keep in mind the fact that x is equal to cos theta. Now, associated Legendre functions. I already mentioned the fact that Legendre equation has two kinds of solutions. The solution when m is equal to 0 is termed as the Legendre polynomial. However, the solution to this Legendre equation when m not equal to 0, the solutions are known as associated Legendre functions. Associated Legendre functions. So, what is the difference between Legendre polynomials and associated Legendre functions? Legendre polynomials are solution to this Legendre equation when m is equal to 0. Associated Legendre functions are solutions to this equation when m not equal to 0. That's the difference between Legendre polynomials and associated Legendre functions. Suppose when the value of m not equal to 0, the solutions are associated Legendre functions, and such associated Legendre functions are denoted as PL modulus of mx. PL modulus of mx. Here we can see the dependence of m on the value of p. That is PL modulus of mx, or we know x is equal to cos theta. Therefore, associated Legendre functions can also be represented as PLM cos theta. PLM cos theta or PL modulus m cos theta. That about associated Legendre functions. Now, associated Legendre functions can have one mathematical equation. For the sake of expressing that there is a mathematical expression for associated Legendre functions, we have associated Legendre functions notated as PLX m or PL modulus m cos theta, or PLX m or PLM cos theta is denoted as, is equal to 1 minus s square raised to modulus m by 2 d raised to modulus m divided by dx raised to modulus m PLX. We already learned about the PLX. PLX is called Legendre polynomial, and this is associated Legendre functions. So, associated Legendre function is denoted by this expression, and in that expression it contains the Legendre polynomial. So, associated Legendre function consists of Legendre polynomial also. If I put m is equal to 0, PLM raised to x will be changed to PLX. That is, associated Legendre function merged to Legendre polynomial when m is equal to 0. Thus, the solution of Legendre equation when m is equal to 0 is simply PLX. If m not equal to 0, this term will work, and we are getting PLM x, that is associated Legendre functions. In this expression, L is equal to 0, 1, 2, 3, etc. and m is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Thus, we can conclude that the expression for associated Legendre function is applicable if not m not equal to 0, and if m is equal to 0, this equation taken the form of PLX, that is the Legendre polynomial. Now, first few associated Legendre functions. We have associated Legendre function PL modulus m x equal to 1 minus x square modulus m by 2 d raised to modulus m divided by dx raised to modulus m of PLX. And in this expression, it is possible to substitute different values for L and m, such that we are getting first few associated Legendre functions. And the first few functions are P00 x equal to 1, P10 x is equal to x or cos theta, P11 x equal to 1 minus x square, the whole raised to 1 by 2, that is equal to sin theta, and P20 x equal to half 3 s square minus 1, and that is equal to half into 3 cos square theta minus 1, P21 x equal to 3x into 1 minus x square, the whole raised to 1 by 2, that is 3 cos theta sin theta. Keeping the fact that x is equal to cos theta. So, 1 minus s square equal to sin square theta. 1 minus s square, the root is equal to sin theta. Thus, we can conclude that the value of associated Legendre functions merged to the values of Legendre polynomials when m is equal to 0. Thus, complete solution to theta equation. The complete solution to theta equation can now be represented as theta of theta is equal to NLM PLM x or NLM PLM cos theta. This here we can see that NLM is a constant that is nothing but the normalization constant. It should be noted that the constant depends on two quantities L and M. So, I put NLM as the normalization constant. This normalization constant can be evaluated by adopting the principle of normalization. We have theta of theta is equal to NLM PLM x. Thus, on integration by applying the condition of normalization, that is integral psi star rt psi of rt d tau is equal to unity. Here integral 0 to pi, since the range of theta is from 0 to pi. The limit of integral diminished it to 0 to pi. So the normalization condition for the theta function is integral 0 to pi theta of theta star into theta of theta d theta. That should be equal to 1. In terms of PLM x, the normalization condition is like this. NLM square integral minus 1 to plus 1. This is because the limit of integration changes from 0 to pi to minus 1 to plus 1, that we have already discussed. This is in terms of theta and this is in terms of x. X is equal to cos theta. For theta, the range is from 0 to pi, and for x, the range is from minus 1 to plus 1. So on proceeding this parameter, we are getting the normalization constant. That is, we have to evaluate this integral modulus NLM square into integral limit minus 1 to plus 1 PLM x dx is equal to 1. This, there is no complex conjugate. This PLM x part is a real part, and hence phi star equal to or theta star equal to theta. Therefore, on evaluating this integral, we will get to the normalization constant NLM as NLM equal to 2L plus 1 into L minus modulus of m factorial divided by 2 into L plus modulus of m factorial, the whole rise to 1 by 2, or this entire quantity is under root. This about the normalization constant of the system. By putting this normalization constant in this equation, we will get complete normalized wave function of the theta equation. The complete normalized solution or complete normalized wave function of theta equation is theta Lm theta. Here it is also clear that the value of theta also depends on the numbers L and M. Theta Lm theta is equal to 12 plus 1 into L minus modulus of m factorial divided by 2 into L plus modulus of m factorial the whole rise to 1 by 2 into PL rise to modulus of m cos theta, and it should be noted that this is for m less than 0. And I have to introduce a correction parameter called epsilon in this equation, and this equation can be corrected like this. Theta Lm theta is equal to epsilon into 2L plus 1 into L minus modulus of m factorial divided by 2 into L plus modulus of m factorial, the whole rise to 1 by 2 into PL rise to modulus of m cos theta. Here the parameter, the correction parameter, epsilon is taken as minus 1 rise to m, where m greater than 0 and epsilon is equal to 1 if m less than or equal to 0. This, in this term, there is no epsilon because epsilon is equal to 1 because the condition is m less than or equal to 0. But when m greater than 0, epsilon has worth, that is epsilon equal to minus 1 raised to m. This is applicable when m greater than 0. If m less than or equal to 0, there is no need for putting epsilon, or epsilon is equal to 1. So this is the corrected, completed, normalized solution, normalized function theta of theta, or this is the complete normalized solution of the theta equation. Now, complete wave function of the rigid rotator. The complete wave function we already discussed in the first part at the time of separation of variable, that psi of theta phi is equal to theta of theta into phi of phi. Here theta of theta depends on the theta function only, whereas phi of phi depends on variable phi only. And theta Lm theta or theta of theta is equal to epsilon into 12 plus 1 minus L minus modulus of m factorial divided by 2 into L plus modulus of m factorial the whole raised to 1 by 2 into PLM cos theta. And the second part, that is phi of phi, that depends on m. Hence I put phi m phi, that is equal to 1 by root of 2 pi into e raised to I m phi. When clubbing together or taking products of these two functions, we will get to the complete wave function of the rigid rotator. The complete wave function of the rigid rotator is given by the expression psi of theta phi is equal to epsilon into under root 12 plus 1 into L minus modulus of m factorial divided by 4 pi into L plus modulus of m factorial into PLM cos theta into e raised to I m phi. This is the complete wave function of a rigid rotator. Now, expression for energy of a rigid rotator. We have defined the parameter lambda equal to 8 pi square IE divided by S cross square. And that is theoretically equal to, lambda is theoretically equal to, we took the assumption also that lambda is equal to L into L plus 1. Hence we can say 8 pi square I by H square equal to L into L plus 1, where capital I represents moment of inertia and L is some constant, namely from range from 0, 1, 2, 3, etc. having whole number values. Thus we get on rearranging or equating 8 pi square I by H square with L into L plus 1, we get energy equal to L into L plus 1 H square divided by 8 pi square I. But in this expression we are having L. But whenever we are discussing with rotational spectroscopy and rotational aspects of the rigid rotator, it is customary to replace L with J. That is, L present in this equation can be replaced with J, and J is termed as the rotational quantum number. So, if we replace L with J for convenience, and it is customary also, and we are getting EJ equal to J into J plus 1 H square divided by 8 pi square I, where J equal to 0, 1, 2, 3, etc. known as the rotational quantum number. Thus, the energy of a rigid rotator is given by EJ equal to J into J plus 1 H square divided by 8 pi square I. Now, we are discussing about a parameter, a new constant that is called rotational constant. We can modify this energy expression by putting a new constant called the rotational constant. We can proceed like this. This is energy in EJ. Energy depends on the quantum number J. EJ equal to J into J plus 1 H square divided by 8 pi square I. And it should be noted that this is an energy term and has a unit equal to joules. And it is more convenient to express this energy term in terms of wave number. That means this energy can be represented in terms of wave number. The relation between energy and wave number is that energy is equal to hc nu bar. hc nu bar, where nu bar is the wave number. That is the reciprocal of wavelength. Energy is equal to hc nu bar, where h is a constant called Planck's constant. So, energy with the jth level is equal to hc multiplied with nu bar j. So, instead of Ej, I can put the value hc nu bar j. hc nu bar j. hc nu bar j is equal to j into j plus 1 h square divided by 8 pi square I. So, nu bar j can be represented as j into j plus 1 h square divided by 8 pi square I into hc. 1 power of h will vanishes and I got the term j into j plus 1 h divided by 8 pi square IC. The term h divided by 8 pi square IC. The term h divided by 8 pi square IC. 8 pi square IC is taken as a constant known as rotational constant B, and that is having unit of wave number. It may be centimeter, inverse, meter, inverse, etc. So, nu bar j is equal to this much. For convenience, in notation using spectroscopy, we have to replace nu bar j by a new term, that is epsilon j. Therefore, epsilon j is equal to h divided by 8 pi square IC, that is nothing but B, and there is one more term in the numerator, that is j into j plus 1. Therefore, the energy levels of a rigid rotator can be represented in terms of wave number as epsilon j is equal to bj into j plus 1, and the unit, convenient unit is centimeter inverse. This is a very, very important expression. This is the expression showing energy levels of a rigid rotator in terms of rotational constant. And also the energy is expressed as wave number. Energy is expressed as wave number because energy proportional to wave number, they are related by this relation also. And epsilon j is equal to bj into j plus 1 centimeter inverse. Here b is a constant, that is equal to h divided by 8 pi square ic and is known as the rotational constant. Now, energy levels can be represented graphically. We have the energy level expression epsilon j is equal to bj into j plus 1. When I put j is equal to 0, epsilon 0 is equal to j into 0 into this term vanishes, that is 0. And I have to find out epsilon 1. For that I have to put j is equal to 1. So 1 into 1 plus 1, that is equal to, so the energy will be 2b. I have to put j is equal to 2. Therefore, b into 2 into 3, that is equal to 6. Energy level will be 6b. Similarly, I can find epsilon 3 by putting j is equal to 3. So, 3 into 4, that is equal to 12b. So, by putting one more example, epsilon 4 is equal to 4 into 5, that is 20b. From this expression, it is clear that the spacing between epsilon 2 minus epsilon, that is equal to 4b, and epsilon 3 minus epsilon 2, that is 12b minus 6b, that is equal to 6b. Epsilon 4 minus epsilon 3, that is 20 minus 12, that is equal to 8b. So, it is clear that the spacing between two adjacent rotational energy levels are not the same. This implies the fact that energy levels of a rigid rotator are not equispaced. This we can represent it graphically like this. The ground state level that I can put, that is equal to 2b. Then the next level I can put as 6b. Next level is about 12b, and the spacing not the same. The further level is 20b, like that. The spacing between two adjacent energy levels are not same. That is, the rotational energy levels are not equispaced. Now, spherical harmonics. This is a very important concept as far as angular part of the wave function is concerned. The complete angular part of the wave function is known as spherical harmonics. Thus, the wave function of a rigid rotator has two components, two angular parts, theta of theta and phi of phi. Hence, the wave functions, the complete wave functions of a rigid rotator are called spherical harmonics, denoted by YLM theta phi. YLM theta phi is equal to theta of theta into phi of phi. We have a theta of theta into phi of phi is equal to psi of theta phi. We already learned, and that is equal to theta of psi of theta phi, or now it is represented as spherical harmonics. YLM theta phi, that is equal to epsilon into under root 2l plus 1 into L minus modulus of m factorial divided by 2 into L plus modulus of m factorial PLM cos theta into a raised to im phi. This is same as the expression for wave function, complete wave function of a rigid rotator, and that is taken as spherical harmonics. Hence, spherical harmonics represents the complete angular part of the wave function. Complete angular part of the wave function, or spherical harmonics YLM theta phi is equal to theta of theta into phi of phi. We can put different values of the spherical harmonics by putting values for m and l. Thus, we will get values of first few spherical harmonics. We have spherical harmonics YLM theta phi is equal to theta of theta into phi of phi. By putting different values of L and M in this expression, we will get the first few values of the spherical harmonics. The first few values are y00 is equal to 1 by root of 4 pi, y10 is equal to root of 3 by 4 pi into cos theta, and so on. So, this about the first few values of the spherical harmonics. that all about the discussion on spherical harmonics. Thus, we have completed the discussion on spherical harmonics and the complete discussion on rigid rotator. That all about this module. Thank you.